Oh, right there, yeah.
So yeah, I don't know. I can hand this out right now. No, because I have supervision today at 12:20, so that's not enough time to review the test. So tomorrow will be fine, but Friday obviously won't. So. Go. Great. Okay. So this is an important definition. You may or may not be tested on it. The idea that an isolated system, come on Nash, let's go. The idea that an isolated system allows neither energy nor matter in or out. So it doesn't exchange matter, it doesn't exchange energy with its surroundings. So if there's any energy released or absorbed, the energy changes completely happen within this isolated system. If something loses energy, something else has to gain that energy. And that is the entire process of calorimetry. In a nutshell, that's all calorimetry is. It's the energy lost by a something is the energy gained by a something. Or vice versa. The energy gained by a something is the energy lost by a something. So we can get a bunch of different forms of calorimetry, and we're going to kind of do some calorimetry stuff today. We're going to do the basics of it. We're going to make two assumptions when performing calorimetry. No heat is transferred in or out. Hopefully that makes sense. We're assuming this is an isolated system. Is this, when I look at this, this is two styrofoam cups stacked on top of each other, and then another styrofoam cup being used as like a lid. Is this a perfectly isolated system? Can energy leave this system? Have you ever held a styrofoam cup and it kind of felt warm? That's energy leaving that system. So energy, it is totally possible. It is 100% possible for energy inside this liquid. Let's say this liquid is 90 degrees Celsius, right? So it's transferring its energy to the styrofoam. Styrofoam is mostly air. But that air and that styrofoam can still transfer energy outside of the system. There is nothing like a perfectly isolated system. That doesn't exist. But we can approximate and get really close to isolated systems as long as we're using appropriate materials. Okay, the change in temperature of a substance is dependent on three factors. So if I had, I don't know, let's say I had an iron ball or whatever. So the material the substance is made out of, iron versus tin, one of these will heat up more with the same amount of energy put into it. The amount of the substance being heated, if I have a big iron ball versus a small iron ball, one of these will heat up more as well. And the amount of heat added to a substance, if I heat one, if I add 10,000 joules of energy versus 10 joules of energy, that'll cause a different change in temperature. We can represent this relationship using the following equation. Q equals mc delta T. That's great for some of you who like equations, and if you want to learn more about that, let me know. But we are going to do unit analysis for this entire unit. Do you remember the methane bubbles activity that we did?
Yeah.
Hopefully, no, we're not going to do it again. If you want to, we can do it outside of class time, but we're not going to take any more class time to do this. Now, what I want to know is, where did the energy come from for us, for the fire to be made? Where did the energy come from for us to do some fiery stuff, Max?
Heat energy from the light.
Okay, so the heat energy from the lighter, it kick-started a reaction, but it did not supply all of the energy for that reaction. what were you holding when you were doing that activity? You were holding bubbles of methane. And methane is CH4. These atoms, when they're bonded together, they have a certain amount of potential energy. So there's potential energy stored inside this molecule. When we react it with oxygen, we unleash that potential energy. We let go, or it releases that potential energy. So the potential energy turns into what? The potential energy turns into what? Kinetic energy. So the potential energy that's being stored in the chemical bonds of the methane molecules, it's released, and it increases the speed of whatever particles are surrounding it. Now, when you did that activity, what did I make you do before we could do the activity?
Cover your hands in water.
I made you cover your hands in water, because when we turn that potential energy into kinetic energy, anything immediately surrounding the fire is going to get hotter. Does that make sense? So your hands will get hotter unless you put a barrier between them. And what was the barrier that we put in between them?
Water.
The water. Now, the water was really, really successful in absorbing the energy from the fire. If we had coated our hands in something different, it would have been a different story. For example, does it take a lot of energy to heat up water, or does it take very little energy to heat up water? It takes a lot, especially when compared to other substances. So if we had been wearing, this is going to sound really weird, but if we had been wearing copper gloves instead of water on our hands, that sounds stupid, but just roll with it. If we had been wearing copper gloves and we did that activity, the heat would have been transferred into the copper. And I want to be very clear. The water got a little bit hot, but the copper would have gotten over 10 times hotter. And so the copper would have increased in temperature, and it might have burnt our hands because the copper got so hot. Does that kind of make sense? Is this idea of we absorbed the energy with the water versus some other substance. So what does it mean to have a high specific heat capacity? Well, it takes more energy to change its temperature. Another way of interpreting specific heat capacity, I would like you to write this down, is that it can store more energy without changing temperature much. Now, that's kind of a stupid way, and I wish I would have phrased that better, but here we are. What the specific heat capacity means, when you look at the units, they're joules per gram degrees Celsius. So there's two ways of thinking about it. Either it takes this much energy to raise the temperature by 1 degree for every 1 gram, or every 1 gram can store this much energy before changing a degree. That's kind of the way you could think about it. It's just two different things. What does it mean to have a low specific capacity? It takes less energy, or it can store less energy before it changes its temperature. And then what material takes the least amount of energy to change by 1 degree? Tin, no problem. Okay, so we're going to do some really basic calculations, and then we're going to go into the lab and we're going to do some what we would call calorimetry, a really basic calorimetry experiment. What is the enthalpy change? So, delta H is what we're going to be using. This is what we mean by enthalpy. and it's measured in joules or kilojoules. Joules or kilojoules. Smart. What is the enthalpy change? Enthalpy, again, is just another word for energy. When 115 milliliters of water is converted from 19.6 degrees Celsius to 98.8 degrees Celsius. The first thing you're not going to really know how to do this very much, but what I want to ask you is, what substance are we talking about?
Water.
And water. And what do you know about something to do with heat and water? What do you know about it? It's got a specific heat capacity of 4.19 joules for every 1 gram and 1 degree Celsius.
So can you only use calculate enthalpy changes like just the ones on our data booklet, like air, polyester, foam, copper, aluminum, iron, and water?
Yes, these are experimental enthalpy changes. Okay. Yep. And so these are the only substances, unless your diploma exam gives you a different substance with a different specific heat capacity, yes, just these substances. Okay, listen up. So what this means is that for every 1 gram and every 1 degree Celsius, we needed 4.19 joules. Now, did we have 1 gram of water? How much water did we have? 150 milliliters. Now, if you don't want to pay attention, that's totally fine, but this is a really important concept. We defined way back in the day, during the time of the French Revolution, when the metric system was first created, we defined every 1 milliliter of water to be 1 gram of water. That was the original definition. So instead of saying 115 milliliters of water, we could say 115 grams of water.
Is that true?
What? Is that technically correct? It is not technically correct. Okay, so what I want to be very clear about, if you had 115 milliliters of pure water at 98.8 degrees Celsius, no, it would weigh approximately 114.6 grams or something like that. So it would be very close, Mark, but this is not an exact conversion, I guess. Max.
So you can't use that rule with any other stuff?
No, that's only water. But in calorimetry, I'm going to go back a couple slides. Remember, we're going to assume aqueous reactions have the same physical properties as pure water. So it doesn't matter if you have any aqueous solution at all. If you have 200 milliliters of that solution, you actually have 200 grams. It's not technically true, but we're going to assume that it's true. Okay, what do we want here? We want the enthalpy change, which is measured in joules. So we have joules. What are the only things you have to get rid of? You have to get rid of grams and degrees Celsius, okay? So I would get rid of grams. Well, we have 115 grams of our water. And then the degrees Celsius, how can we get rid of that?
98.8.
No.
Just times it by 19.6.
No.
Okay.
No. Preston, find the difference. It's the energy change that we care about, right? So what's the energy difference? What's the temperature difference between 19.6 and 98.8?
79.7.
79.8, right?
2.
79.2. So remember what this means. For every 1 gram and every 1 degree Celsius that we change, we must have absorbed 4.19 joules. Now we didn't have 1 gram, we had 115, and we didn't change by 1 degree, we changed by 79.2 degrees. So this will give us
A lot of joules.
how many joules of energy we gain.
Do you want to toss my calculator?
38,000.
Yes. Anybody else need a calculator?
I have a question.
You need a
Enthalpy
Yep. Okay, just give me a raw number. Just give me Max. What is it?
38,162.52.
Perfect. Okay, question.
Are we not just remaking this number?
Yes, you are. This is Q, or enthalpy, equals mc delta T. But the beauty of unit analysis is that I don't have to just look for joules. I can look for grams, or I can look for temperature just by using unit analysis. I don't have to rearrange the equation, right? Okay, is this an appropriate answer?
No.
No. What is our most appropriate answer?
3.82 times 10 to the positive 1, 2, 3, 4.
So the water gained this many joules of energy. The enthalpy change, the energy change, was 3.82 times 10 to the 4 joules. Or, if you want, I want to start kind of being very specific about it. You're going to see a lot of the time we'll measure things in kilojoules. So when you're converting from joules to kilojoules, you just move the decimal 3 times, or you divide by 1,000. So this could also be 38.2 kilojoules, and that would be perfectly fine. They mean the exact same thing, and it's totally fine. Don't worry about it. We'll get used to it. Go through lots of practice. Jordy, I think this is when... no, it's the same thing. Oh, no, it is. Okay, we're good. So we want to know, what is the specific heat capacity of a substance that weighs 36.4 grams and increases from this temperature to that temperature when 8.76 kilojoules of energy is transferred? First thing I want to ask you, what are you looking for? And what is heat capacity, the specific heat capacity measured in? If you don't know, if you have absolutely no idea what specific heat capacities are measured in, you can just look at your data booklet, right? So when we look here, specific heat capacity, oh, right at the top, is joule per gram degree Celsius or joule per gram Kelvin, because degrees Celsius and Kelvin are kind of the same thing. So we are looking for small c, specific heat capacity, measured in joules per gram degrees Celsius. Perfect. What do you want to go on top?
Joules.
Does anything in here have joules?
Yep.
Yep.
Kilojoules.
It's kilojoules. How would I turn kilojoules into joules?
8.76
Divided by 10.
This means kilo means 1,000.
Divided by 10.
So you're gonna multiply by 1,000, or 10 to the 3, right? Another thing that if you don't know how metric conversions work, you can replace the letter K with what value? You can replace the letter K with times 10 to the power 3 if you want to. That's totally fine. So we've got 8.76 times 10 to the power 3 joules. I like to write over 1. You don't have to, but we're just using unit analysis. So are we done with all of the units that we want to on top?
Yes.
Yeah. What do we got to put on the bottom?
Grams.
36.4 grams. And then what's the difference between 25.4 and 54.3? 29.8?
Yes.
Could you have put that all on the...
Totally. I 100% I could have. If we wanted to, we could have put, sorry, that there. Well, it's not working out for me. But I could have put the 36.4 on the bottom and the 29.8 on the bottom. The reason why I don't press them is because I want people to understand that I'm using one value, then I'm looking for another value. And these two things are not related.
Yeah.
They're only related by the problem, but it's not a conversion factor. Okay? This is a conversion factor. All of these things are related to each other based on where I got it from.
Yeah.
Yeah. Okay, perfect. So what's the specific heat capacity?
8.08.
8.08 joules per grand degree Celsius. Good. Any questions about that? No? Okay, there's lots of sample questions. Yeah, I want you to take about 5 minutes and just pick 2 of these questions to do. What? No, we're gonna do the lab. It's just we gotta talk about the lab.
No.
Yeah.
Is there a last thing?
Nope. Just exploratory. We're just gonna kind of have fun with it. That's all. Yes.
I remember someone saying like, no,
So I'm assuming
I'm so
This is the answer.
I'm gonna say 90 years. So what is
Oh, this is what you
raise temperature? Okay, this is 90 years. So what do we want to use? We want to go so I have a theory. So in water, I got like 7 like they give us, I don't know. So what I was
A little bit. I know basketball.
No, it's like 5, but
What's the duration?
No, you get to burn them.
Oh, it's that bad.
In the lab, yeah.
I have a black one.
Oh my god. We have to eat them in the end.
How are you feeling, bro?
Okay, yeah, that should be enough time to do a couple of these. Yeah, yeah. So, if the same quantity of energy, were added to individual 100-gram samples of water, aluminum, iron, what substance would undergo the greatest temperature change and explain? So I'm curious, which of these substances would undergo the greatest temperature change? Max?
Iron would, because it has a lower specific.
Okay, so why does having a lower specific heat capacity mean that it would get hotter?
Because it takes less energy for it to change by 1 degree.
Yeah, the analogy that I've used in the past is if you had these 4 things, and let's say you had the same amount of energy to give up to all 3 of them. So let's say you had 100 joules to give to that one, and that one. What we want to know is which substance could we buy more of a temperature change for, right? So if we had 100 grams, then we wouldn't be able to, we'd barely be able to buy a single degree for water, right? But if we had 100 grams of iron, we'd be able to buy at least 4 or 5 degrees. So, okay. After coming in from outside, a student makes a cup of instant hot chocolate by heating water in a microwave. What is the gain in thermal energy if the tap water is increased from 15 to 95? So this is a temperature change of 80 degrees. So 4.19 joules per gram degrees Celsius, and 250 grams, and 80 degrees Celsius. I don't know what that is. 2, 8, or what? 8.4 times 10 to the 4 joules. Sure. Is this fairly, like, are we having any troubles with this stuff? I don't know, I just see a lot of people on their phones right now.
I just have like.
Yeah, that's okay. So what I want us to do right now is I want us to think about this. The total energy of our isolated system has to remain the same. So if something loses energy, what has something else have to do? gain energy. So the total of the potential and the kinetic energies in a chemical system is called its enthalpy. We cannot measure the total enthalpy of a system, but we can measure changes. If a system loses energy during a chemical reaction, the surroundings must be gaining that same energy. So that's kind of what we were doing there, is the enthalpy change is equal to our mass, specific heat capacity, and our temperature, or our unit analysis. So what I want to be very clear about is that if I had a beaker and it had some sort of hydrochloric acid in it, and we placed a lump of zinc in here, the zinc would react with the acid, and because it's a spontaneous reaction, typically that means that our system is going to be losing potential energy. So the potential energy of our system is decreasing. But again, if something's losing potential energy, its surroundings have to gain kinetic energy. So it's going to lose potential energy, and it's going to release it in the form of heat. The surroundings will pick up that heat, and their kinetic energy will increase. The change in energy must be the exact same if it's a truly isolated system. The decrease in potential energy has to be equal to the increase in kinetic energy. So what we want to do, we want to take an object and we want to burn it. And we want to understand what's the change in potential energy. We want to identify what's the change in potential energy. Now, we cannot measure potential energy directly. We can't measure the change. When I burn this Cheeto, or whatever the hell this is, okay? Yeah, when I burn this Cheeto, you don't want to eat it because I think it's older than I am. When I burn this, what? It's a Cheeto, right? We're good. Okay. When I burn this Cheeto, I cannot measure the change in potential energy. It's not physically possible for me to do that. But what can I measure? The change, if I can't measure the change in potential energy of this thing, I can measure the change in kinetic energy of the water. What we have to do is we have to assume all of the energy from the Cheetos is released in the form of heat. And we have to assume, even though it's not true, we have to assume that the water absorbs all of this energy. We have to assume that. This is what we're going to do in a lab here, and we're just going to make some really basic measurements out in the lab. You want to measure the initial mass of the Cheeto, okay? So, do you have a little bit of room to write some stuff down at the bottom of this? Yeah. Okay. You have to measure the initial mass of the Cheeto. And then what you want to do is you're going to take a paper clip and you're going to kind of fold it so that it makes a stand. Now, there's a really easy way to fold it. Basically, you just want to make a triangle in any way, shape, or form. You want to make a triangle with the paper clip. And then you want to take the side you're not using and bend it up.
Okay.
And then you can just attach. So now you can just attach your Cheeto to here. And then you can burn it. Is that okay? Sorry, it's in the way. Are we good with that? Yeah, it's fairly straightforward. Okay. So then we're going to put that Cheeto. Then we want to put the Cheeto inside like a hollowed out tin can. So I'm going to take a smaller tin can, and it's got some holes on the inside. Why does it have holes on the inside? So oxygen comes in. You don't want to suffocate it, right? And then I'm going to take a bigger tin can and just set it on top. Now, inside that bigger tin can, I want to put 50, sorry, not 100. I want to put 50, the volume of the water is going to be 50 milliliters. What do you know about the water if the volume is 50 mils?
50 grams.
There's 50 grams of water inside that tin can, right? Okay, then all we have to do is light it on fire. So you can take a match or a lighter or something like that. You can light it on fire. You can put the tin can on, and you can measure the temperature change. Now, in order to measure the temperature change, we have two temperatures we have to measure, right? So you need to measure temperature initial.
Why water? It's initial.
V water.
Because it's the 10 that you're measuring the initial, so it's 10 initial.
Yes, initial. And final. That's fine, whatever. And then when the experiment is all over, what I want you to do is I want you to measure one last thing. The final mass of the Cheeto left over. Is that okay? This shouldn't take very long. I want to be very clear. You are very likely to get sooty hands. Okay? Sooty hands. So definitely, if you're worried about your clothes, like I don't care about my clothes at all. So I'm not going to be wearing an apron. But wear an apron. For sure, wear goggles or glasses. Sorry. And then I don't know. Are we ready to go? Does this seem like fairly straightforward?
Yeah, let's
go. You can use Cheetos or Doritos or cheesy puffs. Cheetos there. Hey, can you guys grab the food? Can you grab the thermometer? No.
Okay. Oh my god. It was just me. Don't worry. I was like, who just
Kind of stopped it.
Yep.
Come on, neighbor.
I guess the whole thing.
Who do you want to go with? You don't want to go with? Oh my God. Where's that?
Yes, I'm putting this way.
Can I leave now?
You passed. So
Yeah, sure.
Whoa. Shut up.
I think so. There's so lucky to get a cheat on. That was not my fault.
what happened?
I'm just really smelling Cheeto. Cheeto.
It's so cold.
Where's my phone?
Well, that was fun. About to burn the cheese.
So is the math actually work? Okay.
So I sent a picture of it and I was like, I need to show myself.
Yeah.
And my dad was like, what do you mean?
Yeah.
And then,
Go.
and then my brother was like, means she got a 90 as a figure of speech. She didn't shit herself. She can't do that anymore, but.
Okay. What do you?
Yay. Mind your business, though. Mind your business.
Oh, he's right there.
Answer me.
Well, I hope he was on.
Jesus. It's fine.
Oh, I went to Egypt before I did. Oh, 79.
Oh, yeah.
And
Big
he
flex,
had
yeah.
It's 89.
You call this name.
70. Oh, fine. Whatever.
Doesn't hurt that bad.
And
Have you ever done it with
Got got hot. It almost went up 20 degrees.
Yeah, that's pretty good.
With hand sanitizer? You put like hand sanitizer in your hand since it has alcohol in it. You can light it, but like since there is the layer of like hand sanitizer,
Because it's water, right?
you can just like keep it there for a second.
Never done this before. Okay. What I want you to do, this is the only thing. No, please don't cry. What I want you to do is I want you to calculate the enthalpy change for the water. Why do we care about the enthalpy change for the water? Because the heat's coming from the Cheeto, right? The energy that the water gains is the same as the energy that the Cheeto lost, right?
Yes, sir.
So I want you to calculate the enthalpy change for the water. Go.
I gotta wait for Denver to
Sure. Calculate the enthalpy change of the water.
Wait, the temperature of the paperclip.
Find the enthalpy associated.
Oh,
You didn't get taught that, bro? Yeah, you were.
No, I was daydreaming.
He's in Wonderland.
I was in my place at left with LeBron and we were all getting along.
You're all getting cut off.
There's some goat named Edward Goat.
Bad.
Anyway.
No, just this. But you know, the voice so much. What that is, every kind of person talking about. Tell me if it is.
Bro, look, okay, my parents told me how much they make my dad and my
Bro, this could go down 3 out of 4
or either as much.
Yeah, because he gets his dad to pay Walton.
Just hurts after every
Hey, that's Joseph.
What did Jonas get?
Yeah.
No.
Actually, yeah, no. I'm just kidding.
Our dad, we did it. We lit our Cheeto on fire. No, she doesn't.
We were. Have you watched videos on the new YouTube stuff that's going on? Oh, watching YouTubers probably. Like a lot of people. Because there was a thing that they put in place on TV, you know,
Okay.
and so basically they didn't really enforce it, but they started enforcing it.
Got it?
Yeah.
But you calculated the enthalpy?
Not yet.
Okay.
I'm talking about how a whole bunch of YouTubers and content creators are going to get fined a bunch of money because of a thing called it's like child protection information online or something. It's like in 1988 or something. You know, they're enforcing it a lot more. And basically, if your video isn't marked as like kid under 13 friendly, then if that child gets ads that are personalized to them because of your video, or because their information is supposed to be safe.
Yeah, but the math, this is why I want to know. What is low? What is You need the temperature change of the
I have to go tomorrow.
Okay, Somebody give me their information. Isabel P. Sorry, Isabel P. Give me your information. So the initial mass was 2.5 grams. What was the final mass? 1.2 grams. What was the initial temperature of the water? 22 degrees Celsius. And what was the final temperature? 60 degrees Celsius. Woo! What I'm talking about.
That's not real.
Oh my goodness gracious.
Mr. Walton, the sun's not even
Yeah, that's right. Okay. So, I'll wait. It's okay. Thank you, Matthew. So, if we want to get the enthalpy change of the water, then we should start with, well, first of all, what is enthalpy change measured in? It's joules or kilojoules. Enthalpy change is the same as energy change, okay? So it's measured in joules or kilojoules. Now, do you have anything to do with joules in here? Yeah. 4.19. So we know that every gram of water needs 4.19 joules to increase by 1 degree Celsius. Now, what do you want to cancel out first? You want to cancel out grams or degrees Celsius? Grams. Okay. What mass should I put in here?
50 grams.
Why 50 grams?
That's the water.
Because it's the mass of the water. This is the specific heat capacity of the water, right? So we need to put in 50 grams of water. And then our temperature change looks like it was 38 degrees Celsius. So somebody go ahead and do this calculation for me. Miko, you got a calculator? Can you put this into your calculator, please, since nobody else wants to? I know you got your own. What?
7,961.
7,961 joules. Another way of saying this? Another way of saying this is 7.96, but we should probably use 2 digits. So 8.0 times 10 to the 3 joules, or 8.0 kilojoules. Okay, if the water absorbed 8 kilojoules of energy, then what does that mean? What implication does that have on our experiment? What else do you know about this experiment? The Cheeto or the Dorito or the Cheesy Puff or whatever the hell it was, how much energy did it lose? Does that make sense? The energy gained by the water is the exact same as the energy lost by the Cheeto or the Dorito or the whatever. Okay? So when we come back tomorrow, we're going to do the rest of this, but we're also going to start talking about molar enthalpies.
Just a reminder, chocolate mustaches will be on sale again today.
Make sure you clean up there, please.
And only grade 9 to next students belonging to